Hello everyone, my name is Veselina Kalinova and today I will discuss the link between the velocity profiles of the galaxies and their star formation quenching mechanisms. Based on sample of 238 CALIFA galaxies across the entire Hubble sequence, which is also representing the local universe, we aim to shed light on the two main questions. How do galaxies quench their star formation, and what is the influence of galaxy dynamics on the star formation quenching mechanism? For the goal, we construct two-dimensional emission-line classification called QuestNA. QuestNA takes into account the quenching stages of the galaxies. They represent the rows in the figure, and the nuclear activity of the galaxies, they represent the columns in this figure, for non-active, weak aging, and strong aging class. The main quenching stages of our sample from top to the bottom of the classification are star forming, quasi-nuclear in galaxies, centrally quiescent galaxies, mixed. These are galaxies with no clear pattern in their ionization gas distribution, nearly retired galaxies. Those are the systems with residual star formation within two effective radius, and fully retired galaxies, the one that have no residual star formation within two effective radius. Further details about this classification can be found in our recent paper of Kalinova et al. 2021. Overall, the classification uses the maps of the equivalent width of the H-alpha, we call it double H-alpha here, and certain thresholds 3 and 6 angstroms to distinguish regions which are the retired below 3 angstroms, mixed between 3 and 6 angstroms, and star-forming regions above 6 angstroms. That helps to define patterns in the ionized gas distribution of the galaxies and to find the corresponding quenching stage. On the other hand, the nuclear activity of the galaxies is decided by the Baldwin-Philip-Terulich named BPT diagnostic line ratio diagrams and the WH-alpha value of the galaxy's central pixels. Given this, we look at the distribution of the QuestNA Emission-line classes, and we see that the 6 quenching stages occupy a certain area on the star formation stellar mass evolutionary diagram. The quenching stages look like snapshots of galaxy evolution. The strong aging galaxies in the right panel are distributed within the green valley, while the weak aging shown in the middle panel occupy the low mass and the high mass end of the diagram. It is also surprising that the nearly retired galaxies are the most massive galaxies of our sample, and not the fully retired one. This suggests that probably nearly retired galaxies had experienced merger events in their past. Further, the derived profiles from the equivalent width of the H-alpha CALIFA maps are steeper across quenching stage of the galaxies, from star forming to fully retired. These actually support the inside-out star formation quenching scenario for the evolution of the galaxies. As we shown in our paper Kalinova et al. 2021, the quenching stages of the galaxies correlate with many properties as bulge-to-disk ratio, stellar surface mass density, age, metallicity, and others. Here we try to see if there is some connection between the underlying gravitational potential of the galaxies and their quenching mechanisms. To derive the circular velocity curves of our sample that trace the total gravitational potential, we first analyze the SDSS photometry of the galaxies via multi-Gaussian expansion model and then feed the stellar kinematics using MCMC optimization method. Later, to classify the 238 CALIFA circular velocity curves by their common features, we use principal component analysis and K-means clustering technique to define our 4 main groups. This is shown in the figure in the bottom right corner, where the slow-rising circular velocity curves are shown in a black color, flat circular velocity curves in blue, round peak circular velocity in green color, and sharp peak CVCs class in red. To compare QuestNA and CVC classification, or to compare quenching and dynamical classification, we use the representation of the radar chart between the CVC classes and the quenching stages. This radar chart we name it dynamical compass of quenching stages, due to its similarity to the geographic compass, where the steepness of the circular velocity curve in the dynamical compass increases in clockwise direction. The circles of the chart represent the percentage of the distribution of each quenching stage per circular velocity curve class. We observe quite clear trend that the quenching stage correlates with the type of the gravitational potential of the galaxies. The average circular velocity profiles of the QuestNA emission-line classes show that the CVCs increase their steepness and amplitude from star-forming to fully retired galaxies. Regarding the nuclear activity classes, the circular velocity curve of strong AGN and weak AGN are steeper and have larger amplitude regarding the star formation quenching stage. We also perform an alternative classification based on the distance from the star formation main sequence and applying delta star formation rate thresholds of Black et al. 2016 to separate the galaxies in the blue cloud, green valley, and the red sequence. It gives similar conclusion as the dynamical compass. Here we see that the blue cloud galaxies have slow rising circular velocity curves, while green valley galaxies have flat CVCs and the red sequence galaxies peaked circular velocity curves. Further exploration on this topic will be done with follow-up H1 and CO observation as described here. Preliminary results from EDGE-CALIFA survey indicate that there is a trend of a constant molecular gas mass surface density profiles across the quenching stages, especially above one effective radius. On the other hand, the star formation efficiency of the galaxies is not constant for all quenching stages and throughout their radius. Mixed and nearly retired galaxies show declining star formation efficiency profiles, which is also lower value in contrast to the rest of the quenching classes. This indicates that even there is a molecular gas in those galaxies, something suppresses the star formation in those regions. Single-dish apex CO observations with PI Dario Colombo, which in one effective radius of 472 galaxies, confirm this result of the low star formation efficiency in the retired class galaxies represented by nearly retired and fully retired systems. One explanation could be that AGN in the center of galaxies disperses the gas and prevents formation of new stars, as shown by the image of EDGE-C 1167 that combines the information from resolved H1, CO and CALIFA spectroscopic data. Here we can see that the CO and H1 gas is missing in the central region of the galaxy due to the influence of the strong AGN that had dispersed the gas in these regions. To summarize how galaxies are quenching inside out and with particular quenching patterns. What is the link between galaxy dynamics and star formation quenching? It seems that star formation quenching follows the gravitational potential of the galaxies. I leave you with my detailed summary here, and please let me know if you have some questions. Thank you very much for your attention.